Hello, this is Peter Yerkett. Looking ahead to clustering, which is the next major topic in the textbook after the first two chapters. Uh, the idea is to put together into groups, documents that are similar to each other. So in the vaccine adverse effect slide data set, excuse me, we have rows which represent an observation, a doctor's visit by a patient having something to do with the vaccinations. And one of the columns in that data set is the doctor's notes. But along with other information, we also have the age of the patient, what kind of a shot they had, and a whole bunch of variables describing numeric and categorical variables along with text. So now the question is it possible to group all those 7,000 patients into smaller groups that are similar to, so that the members of a group are similar to each other? And this is a way of classifying what might be done once a patient has been identified as belonging to a certain group. And policies can be written for that. So for that, we need some kind of a measure of similarity between both documents and plain old data with numerical variables, categorical variables, and text variables. Turns out SAS really only deals primarily, in the basic clustering procedure, SAS deals primarily with the non-text variables. For programs like Python and R, they have various clustering procedures. I think in R they're given by girl names like Alice and Sandy and something like that, which may or may not include both categorical and numeric variables, or whether it includes text variables. Those of you that are working with R and Python and Java may have to do a little research as to what the names of the clustering procedures are. I'm going to be using examples from SAS because I don't know what everybody else is using, but I'll be glad to try to answer questions about all of them. So we're looking for some kind of a distance analogy to distance in space. Common analysis goals is to compare entities, documents, and use techniques such as nearest neighbor, which is a distance term. And like I mentioned, we have attribute columns and we have term frequency columns. In a text mining situation, we would have rows that might have both. Let me show you an example. Here is an Excel file with 3 observations, ID. It has some numeric variable, namely income, so this might be the income of the author or the income of the person about which we have doctor's notes. Excuse me. And we have categorical variables. In this case, I happen to pick education level. Could have been dosage that the person got as. And then the doctor's notes get turned into a term document matrix. So we extend the text mining procedure that we talked about in the last set of slides, which resulted in a term document matrix with other variables. And the question is, how do we measure the distance, quote unquote, between these three observations. Well, one of the things that gets done is numerical variables get binned. So we turn a numerical variable, which can have any number between, minus something and 100,000 or whatever, and we make bins or categories, and the categories have an upper limit to the number. So bin number 1, in income category number 1, are all those observations that have less than 15,000 income, and in category 2 is all those that have less than 25,000, and we really should have an income category 3 which is greater than 25,000. So we have 3 different categories, and we now recode the first observation, 29,447, into a income category 1. 29,424 also has income category 1, and 29,380 has income category 2. So now we are beginning to put a vector together so that its first attribute, of course, obviously is an ID, and then the next attribute is whether or not its income falls into category 1 or whether its income falls into category 2. Then we have education categories. Now that's fairly simple. Instead of having a set of words, we identify each category by an education category, and we make partial high school. This is an ordinal variable, so we can order them. 29,447 has bachelor as the income category 3. So for 29,447, income category 0 is 0 because that's not the category. Income category 1 is 0 because 1 is high school, and 29,447 is bachelor. Income category 2 is partial college, so it doesn't belong to 29,447. But income category 3 is designated as a 1 because 29,447 has a bachelor's degree, which is income category 3. So income category 3 is designated as a 1. So what we have done is, instead of having a single variable with 5 values, we have created 5 variables, each with only 1 or 2 which is either 1 or a 0 variable. So the income categories could be hundreds of thousands. Every $100 could be a different income category. We have chosen to just pick 2 income categories, and so now each of these observations, the first 6 variables, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. The first 8 variables, 5 plus 3 is 8. The first 8 variables are the ID, which will not be used in the analysis, so that can remain as 29,447. 2 income categories, whether they belong to a lower income or a higher, and 5 variables that indicate educational level. We do the same thing for 24, oh wait a minute, can't have 2. 2442 has high school, so high school is category 1, so this one should be a 0. And then, and similarly for 29,380 is a high school level. So these are the first 7 variables having to do with income and education, and then the rest of them are just the number of the tokens, and so these are numeric. And so now what we have is, by the time we recode each of these three documents, people, into 0 or 1 categories, we end up with a 12-dimensional vector instead of a 5, 6, 7-dimensional vector. But all the variables are numeric. And so now what we can use is we can use Euclidean distance by just taking the difference in the same variable, squaring it, adding them all up, and taking the square root. And so what we discover is that this observation, 29,447, has a distance of 10 to this observation. And if we look at the first two, the second two, then 29,424 has a distance measure of 13 to 29,380. And we now can use Euclidean distance as squared, and then we take a square root. And what's interesting here, though, is that this number 3.16 or 3.6 doesn't really give us anything intuitive other than saying that, well, 2 and 3, 24, 424 and 380 are the furthest apart, and 1 and 2 are the closest apart. So this is a measure of Euclidean distance that we're pretty well familiar with already. So let's go back to our slides. No, that's not what we want. Here's what we want. And so here's the Euclidean distance slide. We looked at how to turn attribute columns into 0, 1 variables, turn frequency columns into 0, 1 variables, and now we can just apply the Euclidean distance to the corner points of a 12-dimensional square. That is perfectly possible, can be done with calculations. It's not great because Euclidean distance is an approximation, because we got to take a square root, and we don't have a closed form formula for the square root of any number, but it works, and this is kind of the basis of the idea. So now what we would do is we would put documents together whose Euclidean distance is small and separate them into different categories if they're large. Okay, so I think I covered most of what's in this slide, namely to get things into 1, 0 variables. I showed you by demonstration. One of the problems with Euclidean space is that it takes quite a bit of computation to do. Taking square roots, like I said, is a numerically long procedure. But we really don't need to take square roots because we can just leave them as squares, so it's a reasonable way to do it. However, if we've got 7,000 instances, it might take a little while, and we might be able to do better. Another measure is to pretend like every time we get a numerical measure, a numerical variable, that it's a vector in space. So here I have a two-dimensional space, and I have one vector being this solid line, this line, and another vector being this line, and the measure eventually gives us the angle between them. Now the trouble is, of course, that some vector could be much longer than the other. So just looking at an inner product of these vectors, and if you're interested in what inner product means, the last module had a vector matrix Excel spreadsheet that gave you an introduction to that. So what we do is, instead of using the vector as it is, we normalize it into a vector whose length is 1. We just divide all the attributes by the length of the vector, and then measure the angle between them, because now the two vectors are the same size. And that's not such a terrible measure, because we can actually use the cosine of that angle. Again, we don't have to actually calculate the angle, because that's an approximation procedure too. So in one case we use the square of the distance, in this case we use the cosine of the angle between them. And this is a very common measure in text mining. We use the because we can take every vector, every the 600,000 word vector, if there are that many in the doc, and we can take an inner product, and all we're doing with taking inner products is multiplying zeros by ones, or 1 by 1, or 0 by 0, and that's turns out to be actually quicker. So we just multiply the 0 ones, then we divide by their length, and we get a cosine, and that cosine turns out to be a perfectly reasonable similarity measure. A cosine of 1, it means the angles are parallel to, actually one's on top of the other, and a cosine of 0 means they're 40 degrees apart, 45 degrees apart, and they can't get any bigger. So that gives us a measure between 0 and 1 of cosine similarity. And another one, so given this, we can now define similarity measures as minus the Euclidean distance, or 1 over 1 plus the Euclidean distance, and so we get a large d, means they're less similar, so if you divide by the d you get similarity rather than dissimilarity. Or we can take a ratio of min to max distances. So there's actually 3 ways to turn Euclidean space into similarity measures. We can rank, and instead of giving them a numerical value that represents distance, we just give them a numerical value representing rank, and so two documents that are ranked 3 and 5 are closer together than 1 and 8. And so now we have a similarity measure based on ranked. And the other thing is we can just compare whether the same attribute is 0, 0, 1, 0, 0, 1, or 1, 1. So this gives us for each attribute I, for each record, record number 1, we just compare each attribute. So they're either both a 1, in which case we add them to this category. If the first one is a 1 and the second one is a 0, same attribute, we add it up into this group. If the first one is 0 and the second one is 1, then they're added into this group. And if they're both 0, they get added into this group. So now what we have is a coding scheme. And say if there's 600,000 words that describe the similarity, and each one is coded 1 and 0, then these become very quickly. We just go down the length of the vector, compare two variables, two numbers. If they're equal, they get added to 1, if so into 4 categories. And this is an algorithm that's much faster than either taking square roots or taking cosines. And then based on these 4 numbers for each variable, we then add up how many there are that are 1 and 1, that are 1 and 0, 0, 1, 1 and 0, 0. And a dissimilarity measure becomes how many are different, namely S and R. That means if two documents fall into on a variable, one is 0 and the other one is 1, then they're different. So R plus S represents how many different variables there are of the two, and the denominator gives you all the number of variables. Now, if you do this with words, this T, namely both 0, 0, will overwhelm the other three numbers. Most words do not appear in either of the documents. And so a measure that gets rid of that T, because otherwise everything would be small, becomes just the differences divided by the same plus ones and 0, 0, 1 measures. And this becomes, and so this becomes a dissimilarity measure. So a similarity measure now takes this Q, namely when both are 1, and divides by all the other. And this turns out to be a very common measure called the Jacquard coefficient. Very easily computed, because a computer can run through a large array and compare one position in the array with the same position in another array much quicker than any kind of cosine or square root. And so this becomes something of a favored distance measure. So let me go back to the spreadsheet. And what I have here is now, so these two, these are my recoded vectors, and these two are Euclidean squared, Euclidean square root. Inner product is what you use to calculate cosines, and so the inner product measure has 1 and 3 to be the furthest apart, 2 and 3 to be somewhat closer, and 1 and these are apart, inner product. So so these are the cosine similarities. Here we go. So 1 and 2 are similar, 1 and 3 are similar, and the similarity to 3 is small, and that's what we found out. So if we actually calculate the angles between the vectors, we get 50 degrees and 51 degrees between 1 and 2 and 1 and 3, and we get 63 degrees. And if we now take the Jacquard measures, and that's what we need, we need an IOR, we need an AND and an XOR to decide whether one is 0, what the other is 0, whether we have a 1-0 pair or a 0-1 pair. And by the time we put the Q's and the ST's together, we get these measures. So the Jacquard distances of 1 and 2 is very close, similarity. 1 and 3 is furthest apart, and 2 or 3 is intermediate. So this is a demonstration of showing how, and I've given you that same slide with the Jacquard similarity, so you can see what R, S, and Q are. So this is a common way to measure the distance between two documents or two individuals which have both word differences and variable differences. Now SAS does not do Jacquard, because SAS in general will not include the variable, the text variables when it does clustering. The kind of similarities that get attached later on in topic lists. So, but I included clustering in this course because it is an extremely common data mining and text mining procedure. And so we have a choice of how we measure differences between documents and how we measure differences between people, patients, for instance. And I showed you the calculations both in the spreadsheet and in the set of slides. So this is the end of, so I'm going to finish here with the first video lecture on clustering, namely distance measurements, and we'll do the other one in the next video. Thank you.